Good morning, friends. So today I would like to discuss a question, an objective type question from electromagnetic induction. That is a topic from grade 12 CBSE physics. So in this question, a conductor, a conducting circular loop is placed in a uniform magnetic field of magnetic induction or induction d Tesla with its plane normal to the field. Now, the radius of the loop starts shrinking at the rate of dr by dt. Then induced EMF at the instant when radius is r is. So beautiful options are being given. So let's see how to figure out the answer for this question. Well, what we will do is we will just consider some magnetic field lines. So these are some of the field lines. Okay, so we are just assuming the field lines or the magnetic induction is acting in this direction. Acting in this direction. Now, what happens is there is a clue given in our question that the plane of this conductor is normal to the field. So what is this plane? Let's see the plane. So this is our plane. This is our plane. Okay, so this is our circular loop in such a way that the aerial vector of this plane is also passing parallel to the magnetic field. Correct? The aerial vector is also passing, because aerial vector is a vector quantity. How we will get the aerial vector? By drawing the perpendicular to the plane. Correct? So here the plane is normal to the plane. So here we got a clear idea that B and A are parallel. Well, since B and A are parallel, the angle between them definitely equal to 0, correct? Angle between them is equal to 0. Now, they're asking about the induced EMF at the instant when the radius is r. So what happens? There is a clue, another clue given in our question that the circular loop is shrinking at the rate of dr by dt. So we know that in Faraday's law. So what is Faraday's law? So recall the idea about Faraday's law. If flux is phi, then the magnitude of the induced EMF is actually what? It is the rate of change of flux. That is d phi by dt. Since phi is equal to PA cos theta, induced EMF is d by dt of PA cos theta. So what are the three variables in this? One is magnetic field. So the induced EMF is varying with a change in B. Next, change in area. Next, change in angle. Right? But you can see that in our question it is given that the uniform magnetic field. That means B is not changing. And we have already calculated from the clue, the angle between them is not changing. So only one thing is changing here. Only one thing is changing. What is that? The radius is shrinking. So the radius is shrinking, correct? radius is shrinking at the rate of dr by dt. What that indicates? It means that area is changing. So if area is changing, what happens? Obviously, the flux through this will change. The change in flux with respect to time, that is EMF. So induced EMF, the magnitude of the induced EMF is equal to d by dt of what? The area of a circle is pi r square, correct? Into cos 0, right? Because this angle between them is 0. So here b is a constant we can take outside. Even pi also we can take outside. That becomes d by dt of r square. So that becomes eventually, if I'm differentiating, what happens? 2 pi r into dr by dt. Correct. So it is given that the dr by dt is the shrinking rate. So that is the expression for induced EMF. So induced EMF, the magnitude of the induced EMF is equal to 2 pi r multiplied by dr by dt. dr by dt. And I missed the b part. So b is its magnitude of the magnetic induction. Correct? So which option will give our answer? 2 pi r 2 pi r into d into dr by dt. So which option? Option number 3. Option B is the right answer. So that's all for the day. I hope you got the idea. So this is how we are doing this question. Very simple concept. Using the concept of Faraday's law, we solve this question. Thank you very much. So we'll meet again with a different video.